Okay, good to see people starting to join. Let me do a little bit of housekeeping whilst we wait for everyone to arrive. Welcome to this Value in Energy Data webinar by Energy Systems Catapult. Great to have you with us. Please keep your camera and microphones off. We're recording the webinar and it'll be shared on YouTube afterwards, and we'll circulate the slides as well. The way that we run these is if you have questions during the talk, please do put those in the chat. We have time for questions and answers at the end of it, and lots of good discussion. So yeah, please pop your Q&A in the chat and we will get to those at the end. The topic for today is Aeolus, an intelligent wind farm management system. And we have with us two presenters from the University of Warwick. So Professor Xiaowei Zhao is Professor of Control Engineering at the University of Warwick, where he established and leads the Intelligent Control and Smart Energy Research Group. He's the director of the SuperGen Network Plus in Artificial Intelligence for Renewable Energy and a co-director of the SuperGen Offshore Renewable Energy Hub. And with him is Dr. Hongyang Dong, who is an assistant professor at the University of Warwick. And his recent research centers on AI-powered wind farm control, where he develops reinforcement learning algorithms to significantly enhance overall wind farm efficiency, which is what we'll be talking about today. So thank you very much for joining us both, and over to you, Xiaowei.
Thank you, Sam, for the invitation and introduction. Good afternoon, everyone. We are delighted to be here today to talk about our intelligent wind farm management system, AIOLUS, which combines AI and Aeolus, the Greek god of wind. So you can see this name reflects our ambition to reshape the wind energy sector while cutting-edge AI technology. First, I would like to give a brief overview of our group, ICSE, Intelligent Control and Smart Energy. Here are the core group members of the ICSE team. In addition, we have over 20 PhD students and postdocs, and collaborated with more than 30 industry partners and 20 academic institutions. We work on AI-based modeling, prediction, digital twin, and control technologies with application in offshore renewable energy systems, hydrogen systems, smart grids, and autonomous systems. We have built 3 labs corresponding to the 3 of our research areas, which are the autonomous system labs, the renewable energy integration and the smart grid lab, and the offshore renewable energy lab. Here are the labs. The hydrogen lab is part of the renewable energy integration and the smart grid lab, but it is located outside the building for safety reasons. Next, I will introduce our research area in each lab. We start from our autonomous system lab. We designed and built the flexible aircraft and quarter-rotor UAV with their simulators. The aircraft has a high aspect ratio wings. The simulators can be used to do controller-in-the-loop test before the controllers are developed to the real autonomous system vehicles. We also have 3 small UAVs and 1 underwater drone for algorithm testing and all computer vision integrations. Other research in this lab includes aeroelastic modeling and control, path planning and trajectory control, as well as safety critical control. Now let's move to the area of renewable energy integration and the smart grid lab. The facility in this lab allows us to do real-time hardware-in-the-loop tests for the grid integration of renewable energy and hydrogen systems. Other research in this lab includes modeling, stability analysis, control, and ancillary services. This is our offshore renewable energy lab. It is a computation and a simulation lab. The work in this lab covers modeling, prediction, digital twin, and simulation, as well as power generation control and structural control. The research conducted in this lab results in AIOLUS due to a few years of efforts with the support from several past and ongoing projects. I now would like to briefly introduce two of them, and the third one will be introduced at the end of the presentation with a video. The first project is CPAIR, CPGen Network Plus in AI for renewable energy. CPAIR was founded under the EPRC CPGen program that was set up in 2001 to deliver sustained and coordinated research on sustainable power generation and supply, focused on key research areas. CPAIR aims to establish a world-leading network connecting academia, industries, and policymakers across the spectrum AI for renewable energy. This includes generation, storage, transmission, distribution, and demand-side management. We will create the condition in which AI for renewable energy can be promoted much more rapidly than at present to boost the development and the deployment of renewable energy, accelerating the transition to a clean energy future. We have 4 investigators and 33 project partners across many sectors, including energy, AI, data, software, consulting, and policy making. Based on the current critical mass and the emerging research gaps, we proposed 6 research themes to steer our activities, which includes prediction, digital twin, intelligent control, smart integration, intelligent robotics and autonomous systems, and robust and trustworthy AI. The second project is called ARCONIC, which stands for Smart, Aware, Integrated Wind Farm Control Interacting with Digital Twins. It's a 6 million Horizon Europe RRA project involving 7 academic and 7 industrial partners across 7 countries. The core of ARCONIC is to develop an integrated wind farm control system supported by next generation of modeling and simulation tools, advanced digital twin, AI-powered lifetime management, and solid validation. Now let's explore AIOLUS. The growth of wind energy is astonishing. It now accounts for nearly 30% of the UK's electricity, and the government plans to further big push with the goal doubling onshore wind capacity and increasing offshore wind capacity fourfold by 2030. However, there are challenges, which of course creates opportunities. One of these is to improve the operating efficiency, but this will depend on the technological breakthroughs. Because traditional methods are unable to overcome existing bottlenecks and scale in the way that is required to meet the challenges of larger and more complex wind farm. AIOLUS address many challenges. For example, mitigating wake effect. The wake from upstream turbines, which you can see here, slow the flow through those further downstream. This can significantly reduce the annual energy production. The result of AIOLUS is improving operating efficiency. Applied to existing capacity in the UK, this improvement in performance is equivalent to adding several free wind farms totaling 1.6 gigawatts. To physically build this capacity would cost around £3.2 billion. And if applied to the government targets for the expansion of the industry, 9 billion by 2030. Another way of looking at this is it would lead to an annual reduction of 2 million tons of CO2 emission based on the current capacity. So this is equivalent to remove 400,000 cars from the road. AIOLUS is an intelligent wind farm control system combining next generation of modeling and digital twin technologies supported by rigorous validations. Today, we will focus on the control system and its validation. I will now hand over to Hongyang to present this part. Thank you. Hongyang, over to you.
Thank you, Xiaowei. To make it easy, let me directly share the screen from my side. And can you see my screen nice and clean in the full screen mode?
Yeah.
Yeah.
Okay, great. Yeah, thank you. So at Xiaowei's side, Aeolus is centrally in control, as you can see here, and it's also powered by several things. You can see next-gen modeling tools and also AI-powered digital twin, and quite a lot of validation methods. And today our focus is on the control system design. So actually we have been doing research in this area for over 5 years, and we do both farm level control and turbo level control. And that's also the case for Aeolus. But today we may focus more on the farm level control part. And for this part, we built our control algorithms based on reinforcement learning. And because I don't know whether today's audience, attendees, whether you have background in AI or control system designs or not. So I think I'd better start with a very brief introduction to reinforcement learning. So reinforcement learning is a booming artificial intelligence area, particularly during the past 10 years. And to summarize its key function, I would say it can learn to make decisions without needing a full model of the environment. So that's quite different from the traditional control system designs. I think about a very simple mass rain damper system. So we can call it a white box system, which means we know the exact analytical equation of such a system, and it's very easy for us to build an ordinary differential equation to describe it, and then design control system controllers to control it, right? And advanced control methods can handle gray boxes, which means think about aircraft. We can model part of the system, but we actually have uncertainties and also external disturbances that influence the accuracy of the system. But luckily, some advanced control methods like robust control and adaptive control, they have the ability to handle such gray box systems. But there are some limitations for advanced control systems, like controlling black box systems. So think about, I think a very good example of a black box system is a video game. So think about a video game. If you're familiar in modeling and control system design, think about how should we use a bunch of, let's say, equations to describe a system, such a system, to describe a video game. So it's almost impossible, right? Not to mention control, such a video game based on no matter traditional or advanced control methods. So that's, you can see the limitations of the control engineering sector, and this is where AI steps in. So a key feature, a very good feature of reinforcement learning is that it can control black box system. And how that's possible is, I think about as human beings, when we learn how to walk or how to run, we don't need to build a model for ourselves first, right? We directly interact with the environment. We use our eye to take observations, like, see how other people try to walk or run, and then we take a step, right? We take an action. So this action can be good, can be bad. So we can fall down, but through such a trial and error process, and little by little, we will learn how to walk and run, right? So that's a learning process of a small baby. So such a process, as summarized here, you see we take observations, we interact with the environment and take observations from the environment, and then we take actions, again, interact with the environment. And through such a loop, the environment will tell us, oh, whether the step you move forward is good or bad, whether you fall down or you can, oh, stand up a little while. And so that's what we call a reward. So through such an observation, action, and rewards loop, and also the trial and error experience, we can, as human being, we can finally learn how to handle many very complex tasks. And reinforcement learning actually follows such a design. It take observations from the environment, make actions based on what we call the actor network, and also collect rewards from the environment, also from the environment based on the actions the AI agent made. So through such a process, it can little by little learn a very good strategy to handle different tasks, such as playing a video game. And I'd like to show you some advancements in reinforcement learning very quickly. So first one, I guess many of you know that is the AlphaGo and also AlphaGo Zero developed by Google DeepMind. And it is very famous because it's quite a very important milestone in the development of reinforcement learning. So AlphaGo, which is an AI agent that managed to beat some of the best professional human players in the board game Go. And also another most very recent example and very famous example is ChatGPT. So the preliminary focus of ChatGPT is on natural language processing. But one of the key factors that make ChatGPT so much better than other large-scale AI GC models is reinforcement learning based inner loop. So what they call human in-loop reinforcement learning. And such a loop allows humans to evaluate the answers generated by ChatGPT. And so basically they mark the answers generated by ChatGPT, and such a refining and improving process is turns out very helpful, help ChatGPT to perform much better than many other chatbots. I'm sorry. So you can see reinforcement learning is a powerful AI tool. So what in our work, what we did at the very beginning is that we leveraged this booming technology and design new algorithms for wind farm control tasks subject to strong weak interactions between turbines. And so as Joey said from this photo, so this is a very famous photo showing a wind farm at Denmark. And why it's very famous? Because it can clearly show us the wake effect among different turbines in a large wind farm. So basically, after upstream turbines extract power from the inflow of wind, and then it will lead to a wake behind it. As you can see from here, the cloudy style thing as wakes generated by different turbines. And such wake effect can significantly influence the turbine downstream, influence their power generation process, because wake usually has reduced the wind speed and increased the turbulence level. And another feature of such wake effect, it can be cascaded. You can say the wakes induced by different turbines, they can combine and propagate further. And at the end, if you have a very large wind farm, the wake effect can be very complex. And currently, the way for most of the wind farm operator to operate to handle such a large wind farm is that they apply the so-called greedy control strategy, which means that each turbine just focus on its own power generation. So it's in a greedy way, and don't consider the potential influence of the wake induced by them. And through such a strategy, you can say it's definitely far away from optimal. We actually must consider a more collaborative way for turbines within a large wind farm, so that when they doing optimization, operation, they need to think about the potential influence to other turbines. And our goal is to optimize the farm-wide power generation from a long-term perspective. Okay. And we started this research area, as I said, about 5 years ago. And in our initial design, we utilized the yaw control to achieve wake steering. So basically, we control the yaw angle of upstream turbines, so the wake, the direction of the wake can be steered a bit, so the downstream turbines can suffering less from the wake effect generated by upstream turbines. And in this design, we improved a famous reinforcement learning control algorithm, which is called DDPG, Deep Deterministic Policy Gradient. And we improved by several elements and also a so-called reward regularization module to address the reward normalization issue under different wind speeds and yaw angles. And the whole method here is data-driven and model-free. And moreover, we also designed a special adaptive control methods to achieve high precision yaw maneuver under even unknown parameters for the yaw actuator. And some results shown here, we carried out high fidelity simulations with the SOFA simulator developed by NREL to test the effectiveness of our method. And for a small wind farm with 6 turbines, you can see after, so we first do the pre-training and then we do fine-tuning. And after 3 fine-tuning iterations, we increased the whole farm's power generation by around 10 to 15% compared with the greedy strategy. And this work is was the first one in Europe that designed a reinforcement learning strategy for wind farm control. And after this initial design, we hope to further achieve like better robustness against the time-varying wind speeds and directions. And we hope to reduce computational cost in the training stage to enhance our algorithms' applicability to large wind farms. And also we hope to achieve better adaptability to different scenarios. So based on these needs, we then developed a series of different wind farm control methods, and we tested them with different wind farm simulators. So some of them are high fidelity and some of them are control oriented. And in all these case studies, we noticed that our algorithms can achieve better performance compared to no matter the greedy strategy or some of the recently designed advanced wind farm control methods. So that show us the power of reinforcement learning and encouraged us to explore further in this area. And a quick example of our design from the theoretical level is that we developed what we call robust different reinforcement learning method for wind farm control. And here, the key difference from traditional reinforcement learning, which stick to the so-called actor-critic structure, is that we also designed a distractor module to try to estimate the worst case due to the varying of wind speeds. And based on this worst case scenario, we try to get better control policy to enhance the overall control performance in wind farm control. And additionally, we also designed a new sampling strategy to enhance learning efficiency. Then, under the influence of disturbances, our algorithm showed better performance than DDPG. I forgot to mention that DDPG is actually a very famous algorithm and it's a derivative algorithm of the fundamental one used within AlphaGo. Okay. And then after we developed so many control algorithms, we think about how should we move forward to achieve internal test and also field tests in the future. So we carried out several recent designs, and in which we consider what we call both online and offline deep reinforcement algorithms. So online reinforcement learning algorithms means that, when you have an AI agent, reinforcement learning agent, you need this agent during the training stage, you need this agent to interact with a simulator or a real environment. For the wind farm control case, it's impossible to directly interact with a real wind farm during the training stage of your algorithm. So here, online means, you need a simulator to interact with your AI agent, and then let the AI agent to learn from such interaction and little by little improve its control performance. And in contrast, offline reinforcement learning means, when you don't have a simulator, you just have some data set, let's say from no matter generated previously by a simulator or from the SCADA data of a wind farm. Then when you don't have the option to build a simulator with such a data sets, how should you extract the most helpful information from the data sets you got and then train your controller? So different from the online reinforcement learning method that directly interacting with simulators, offline reinforcement learning just use the data sets that can pre-collected and learn the best control strategies that it can learn based on such offline data set. And recently, during the past 12 months, I would say especially during the development stage for Aeolus, we considered both online reinforcement learning, which we are quite familiar during the past several years, and we also consider offline reinforcement learning, which is also new thing for us during the past actually 12 months. Okay, so I will talk a bit more about our offline reinforcement learning design. And it incorporates pre-collected wind farm data, as I said before, which is what we call offline data, to enable learning without intensive interactions with the environments. And a key feature of it is that we designed a GAN-based structure. So GAN means generative adversarial network, and this structure refines control strategies through adversarial training. And we also have a policy divergence estimation module, so which mitigates distributional shift and enhance generalization during training. And so our method was tested on a typical 3x3 wind farm layout, and the result showed that the weak effects were mitigated, leading to improved farm-wide efficiency, and our algorithm achieved higher cumulative reward than the greedy mode and also other reinforcement learning baselines. And our approach also outperformed some other offline reinforcement learning methods, demonstrating better policy learning and sample efficiency. Okay. We also tested our method on random wind farm layout, as shown here, and also the sea power layout, as shown here. And the results show that our method adapts well to different layouts, proving its real-world applicability. And compared to other advanced wind farm control methods, such as preview, weak steering, and also the another weak control method, which is called FWAC, our approach achieved the highest farm-wide power increase. Okay, so after we carried out so many theoretical designs, we then finished the first ever wind tunnel test for AI-powered wind farm control last November, and we prepared a video to show you the result we got from the field test. Yeah. So we carried out our field test at Europe's largest wind tunnel at Milan. Very good for the wind tunnel. As you can see, we got a very large turntable in the middle. So when this turntable rotating, it can mimic the change of interactions. That's a very challenging environment for the design of AI-powered control method. Okay, some videos from our test. We carried the test for roughly a week, representing about 100 days at full scale. You can see here we got 6 scale turbines to form a small wind farm. Okay, so here is a highlight for the internal test. As I said before, we test both online and offline reinforcement learning algorithms. And the online one uses a multi-agent step, and the offline version builds on top of all the algorithms we test during the internal during internal test and also previous offline methods, but with extra improvements. And we also tested several other advanced wind farm control methods during our internal, and we noticed that we outperformed all of these methods. So the key takeaway is that we saw more than 10% average power gain under changing wind directions. And at some peak scenario, we saw over 25% power gain, so which is really promising, and we are very excited about the result we got. Okay, and yeah, and another very interesting thing that we realized during the internal test is that when you have wind direction change around 0 direction, so sometimes when you do yaw control, it will give you, let's say, at 1 second for some conventional methods, it asks you to yaw in your turbine to 20 degree. And then when the wind direction suddenly change from negative to positive, the controller may ask you your turbine's yaw angle to shift from let's say 20 degree to negative 20 degree. So that's definitely not necessary and can influence the lifetime of the actuator of the yaw part of the turbine, right? And we designed what we called a transformation module to avoid such unnecessary yawing during weak steering. And it turns out it performed very well. And from the DEL side, we achieved less DEL compared to other advanced wind farm control methods, but don't have the function to handling wind direction change around 0 and the unnecessary usage of yaw actuators. And here, these two figures also show some additional results we got from the internal test. On the left-hand side, it shows the average power gain of the wind farm across different wind directions, illustrating the range and variability in performance improvements. And on the right, the bar chart displays the power gains for individual wind turbines in a row across different wind directions, highlighting their contributions to the overall energy output. And as Xiaowei mentioned before, so our results, all of our results are funded by 3 projects, and Xiaowei already introduced the Super Airy and also Iconic. So the 3rd project is the Manchester Finalist Prize. We likely got it last summer, and it was announced by the Prime Minister. And we got a video from these to do a quick introduction for this project. Yeah.
So what we're doing with Aeolus is actually teaching the AI how to play the wind farm game, how to operate the turbines most efficiently, how to keep them safe, and how to maximize benefit for society.
And by applying the AI systems that we've created, we're optimizing the power generation that we're getting.
Aeolus will have a massive real-world impact that people will actually feel in their daily lives. Instead of just building more turbines, Aeolus helps to get more energy from the wind farms we already have.
At the core of Aeolus is its smart control technology, which is then supported by the modeling and digital twin, all powered by cutting-edge AI.
It increases wind farm efficiency by at least 5%. That's equivalent to powering 1.25 million homes every year with clean, free electricity. In 5 years' time, we believe we can be deployed on hundreds of wind farms around the world. Perhaps most importantly, we'll be able to have tailored bespoke solutions for every turbine model and manufacturer, helping wind energy scale faster, cut cost, and become even more reliable.
Yeah, thank you. So the next step for us for the developing of Aeolus is a field test. We already scheduled a field test with the sea power wind farm at the North Sea, and hopefully we can show the result very soon after the field test done. Yeah, that's all from us. Thank you very much for listening.
Thank you very much. So please do feel free to put questions in the chat for our speakers, but I'll kick us off. So do you see a difference in performance, but kind of gains, like efficiency gains, between the online and the offline? So when you did the wind tunnel test, was there a big difference between those two methods, or did they perform similarly?
Oh, Sam, thank you very much for this very interesting question. Yes, we did notice different. Actually, the offline reinforcement learning method performed best among all other methods we test during the internal test. One reason is because it actually leveraging the data from all other methods. So think about it's kind of like, you try to do automatic driving machine, and then you try to have all the information, all different data sets based on the driving experience of different people. And the AI can leverage such information to try to get a better, driving performance. So it's quite similar for wind farm, in our case, for wind tunnel test. So we improve the offline reinforcement learning little by little. At the very beginning, we just used some pre-collected data from the wind tunnel based on their previous tests. And we got the offline reinforcement learning method trained based on such previous experience or data sets. And when we carry out the wind tunnel test, we got more data. And with this more data sets, we then fine-tune, we then improve our offline reinforcement learning. And at the end, we noticed that it performs better than its training data set. And about the percentage, I would say it's like we achieved like 0.5% increase. I mean, like for the online one, if we achieved the 10%, then for the offline one, we achieved 10.5%. So that 0.5% seems not much from the from the number, but actually for wind farm control, it's a huge improvement. Actually, yeah.
Yeah, really interesting. That's the opposite of the direction I would have expected. I would have expected the online to kind of perform better. So. But I can see why now that you explain it. I'm like, I can see why, yeah, the offline might. Great. So Steve asks, do you have an estimate of the effect that wind management and kind of like improved efficiency of wind farms will have on wind curtailment rates? So have you thought much about that?
This is not in the scope of the Aeolus. So here we mainly focus on the efficiency improvement. But we do have other projects. We work on how to combine wind farm together with hydrogen to help the wind curtailment. Yeah, it's in different projects. We have a EPRC project working on this area.
How well does this work at lower wind speeds? Like how much of the kind of like efficiency benefits do you see at lower wind speeds rather than at kind of the higher wind speeds? Presumably the benefits drop quite a bit because the wake effects drop.
Actually, if in region 3, actually the effect is minimal, because if for example, if there in that region, although there's a big wake effect, but it's run at full capacity, so we didn't gain much. But in that region, it's the load reduction is become very important. So the main region that or this system work better is in region 2.
And what, for people who aren't familiar with kind of wind, what do you mean by region 2, region 3?
Okay, region 2 is like when the wind speed is below rated, so each wind turbine have not reached its full capacity. Like for example, if a 5 max wind turbine, the wind speed can only allow it to work at below 5. That's region 2. Region 3 is wind speed is above this rated speed. Yeah, at a very low level, of course. I mean, if for example, at the bottom section of region 2, the wake effect is not significant. Of course, it will the effect of the system is not significant, because yeah, it really depends on how much wake interaction. Yeah.
Great. Robbie Morrison has a question. Any thought on adding bird interactions to the kind of environment and the kind of reward for the reinforcement learning to kind of avoid casualties? Any thoughts on that?
Yeah, it's very interesting. It's a good, right? If later we include this in AIOLUS, it's very interesting topic. Actually, last week we had a annual meeting for the Iconic project. So we talked with the wind farm operator, Sea Power. They also mentioned this point. Yes, it's a great point. Yeah, we will include this into the future development of AIOLUS.
Interesting. Yeah, one that people are increasingly prioritizing. I've seen other wind farm optimization that happens more in the planning stage, and so people kind of like try to optimize the turbine layout to reduce wake effects to start with, and then obviously you're kind of going on top of that and optimizing during the operation. Have you done any kind of work or analysis around whether the benefits of AIOLUS kind of shrink for well-optimized wind farms at the wind farms that were optimized well at the start, or whether it's fundamentally something that no, we expect similar size benefits for most wind farms because it's something you can only do at an operational phase?
I think the next stage of our research is we are combine the wind farm optimization with the design stage. It's a co-design.
Yeah.
And then Steve asks, could these methods easily be extended to tidal farms? Do they have the same kind of wake effects? Do you think they'd be applicable in the same kind of methods?
Yeah. Yeah, it's definitely I mean, it definitely needs to be changed a bit, because all our algorithms they are not like directly employing of like existing ones. Not that we have our tailored designs for wind farm control problems, and for tidal farms, because they share so many similarities with wind farm. I guess many like application-oriented designs can be also applied to tidal farms. So I would say definitely can be expanded to tidal farms. Those additional application-oriented designs need to be considered. Yeah.
Great. Really interesting to hear about the sea power kind of trial. Can you tell us a bit about, in terms of like actually scaling to the point where lots of wind farms are using this? So like assuming that the sea power trial works, how do you think you're going to get to lots of wind farms around the world using this? Do you have kind of like plans for how to scale it up around the world?
As shown in the Manchester Prize video, we work closely with REST group. So they manage over 220 wind farms in many countries of the world. So we, after the sea power trial, we will work closely with. Actually, we already started to work closely with the REST. So if sea power demonstrate this control method works well, and it's a good opportunity we scale up it together with the rest.
And what kind of what does the process look like for applying it to a new wind farm? How much kind of data is required from that new wind farm versus how much kind of control strategies that work on one wind farm kind of like transfer relatively easily to another one?
Oh, from the methodology side, it's within the same pipeline, but for different wind farm, definitely we need their data and also their layout. Their they have different turbine type. Yeah, so we need to for different wind farms we need to carry out some further designs. But for the fundamental theoretical part for reinforcement learning, it's within the same pipeline. Yeah. Mm-hmm.
Right, and I know from kind of previous interactions that a lot of this was underpinned by some of the advancements in simulation that you've been working on. Do you want to just briefly touch on those and explain to people why those were important for this kind of application?
Shall we please?
So sorry, can you repeat?
Do you want to just explain to people a little bit, I think kind of talking about the GPU acceleration of some of the simulations and some of the kind of like other techniques for accelerating the simulations and how that enabled you to develop Aeolus?
Okay. Basically, in the wind tunnel test video, there's at the end there's a sea power wind farm simulations. That simulation was done by us with GPU technologies. It's a high fidelity simulation by GPU. It's largely speed up the simulation speed by GPU.
Right. Yeah.
This one we have not published yet. Yes. Yeah. So we are finalizing this work. That's why we didn't. We have not. That's why we just show the video. So yeah. Later, after we finish the paper, we will provide more details.
Great. Well, thank you very much. And yeah, this is one of those areas where I'm really excited about it from a decarbonization impact perspective because of the ability to scale relatively easily. We don't need to build lots of new wind farms, but if we just adopt different control strategies via software, we could get benefits relatively quickly. So a question from Robbie, which is obviously we use coarser energy systems models to kind of predict energy demand in the wider energy system and energy generation. Can we simplify these control strategies and kind of characterize their performance for use in those models so that we can see how wind farms would perform in different weather conditions differently if they were operated with these control strategies?
Oh, yeah, that's a very interesting question. I mean, when you use the word coarser, I'm not very sure, it's like to what level. But I need to think about whether you need like what we say control or optimization. So that's quite different based on the, I'd say the timeline, the time interval you need it. So when it's very long time interval, then maybe it's better to go to optimization. And the reinforcement learning can also do optimization. So that can be done, but then you also have many other choices. And but if, let's say, the time interval you consider that it's still a bit intensive, let's say second level or few minutes level, then reinforcement learning it's still it's definitely powerful for such scenario. So when you have longer time interval, it's maybe not worth to consider, because reinforcement learning sometimes, though in the implementation stage, its computing cost is okay. It's maintained at a similar level for advanced control method, and even less than, let's say, some control methods like model predictive control. But in the training stage, it's very computational costly. So for your application scenario, I think the first question is to think about whether you need optimization or optimal control. And if it's optimal control, then reinforcement learning is definitely, but from the theoretical level, it can do both. Just think about whether during the training stage, it's whether worth to do so. Yeah. Mm-hmm.
That's a really useful distinction. I guess there's another angle to the question, which is, if you think about like our whole energy system models in lots of different contexts, but like the system operator will have a model of like what wind will do in like what wind generation will do in different contexts and that kind of thing. If this really if Aeolus is kind of like really effective in increasing generation by 10% or like up to 25% in different circumstances, how easy do you think it is to alter the system operator models or the kind of like big national models to account for the fact that we now, like, wind is behaving differently, like wind generation is behaving differently from the way that it has in the past? Have you given any thought as to kind of like characterizing it of like, oh, in these weather conditions, you'll get this improvement or anything like that, so that people can plug those assumptions into their kind of bigger picture models?
Here, because according to the national strategy, I mean, the capacity of the wind will increase anyway. For our case, is we try to through this method, this is like add some free virtual wind farms to reduce the construction cost. And in terms of grid integration side, is currently the AIOLUS do not have the grid integration part, but this is another active area or team, as I just show you, or smart grid lab. So next stage will include the grid integration, how to use a wind farm to provide the ancillary service to the power grid. We integrate this part into the AIOLUS.
Great. This is a really naive question that reveals my ignorance of wind generation generally. But when you talked about the type 3 or kind of the stage 3, I forget what the word was, but the like wind greater than the maximum capacity, is there benefit to a wind farm of having all turbines operating rather than turning some off in the higher wind speed? So currently you're doing wake steering to increase the average generation of the turbines, and kind of like weight that more equally across the turbines. But is there benefit in actively using wakes to decrease the load on some turbines, and to kind of like allow them to keep generating when the wind speeds are high? It's, as I say, a naive question, but is there any benefit in kind of using it to in higher wind speeds to change things like that?
Wow, that's a very wide question, but very interesting. First of all, usually wake is, will increase loading level, and partial wake will also even sometimes have higher impact. So when we do like yawing for wind farm, actually also consider the loading effect. So that's a factor that we considered in our control system design. And yeah, I have to say another thought in our mind is that whether we can do like load distribution among all the turbines in a farm to try to make the lifetime, I mean, from the farm-wide level also be maximized. So that's yeah, so that's a very interesting question. And yeah, what you mentioned, the region 3 is like above the rated power, and when the wind speed gets stronger and stronger and stronger, it's also region 4. So region 4 means you can no longer handle the potential risk induced by the very strong wind. Then many of the turbines just shut down. And so this area is also an area that we are working on. We consider what we call soft cutoff. So we don't immediately cut off the power from the turbine because from the grid side they really don't like this pattern, right? So we think about whether we can create a better curve, especially for some designs of some new turbines, to do a soft like dropping of the power and get this thing better. Yeah.
Interesting. Final question then from me. So you talked about it being computationally intensive in the training phase. What kind of computational resources have you been using for the training? Like when you say it's computationally expensive, give people an idea of the order of magnitude or the cost of that.
Wow, I mean, the most costly part is actually simulating. The main try to simulate wind farm is very computational costly. And for the control part, it's I mean, compared to the simulation, I would say if you have a common GPU or you have a workstation with 40 cores, so that's enough for a small wind farm to finish the I would say for wind farm is 10 to 20 turbines for you to finish the control part of the training. And we also designed several methods to leverage the cost during the training stage. Like we think about, when you have a very large wind farm, whether we can divide the whole wind farm into several turbine groups, and based on the interaction level in terms of wake effects of different turbines. And then with those small groups of turbines, you actually can do like parallel training for them. So that's something we think about. We designed to leverage the training cost during the for reinforcement learning based control system design. And yes, that side, so the training cost for I mean, the training cost is kind of high, but I would think it's acceptable. And when it comes to the implementation stage, actually the computational resources requirement is not so high. We actually can apply, let's say, a reinforcement learning method after training. We can apply the neural network to generate the control signal to a PLC. So that's possible. Is that kind of like we do not change the hardware setting of all the current turbines. We can manage to apply our method to the hardware they already have, like Beckman. Yeah.
Just
Really?
sorry. We have wind farm models as a different fidelity, like low, middle, and high fidelity. We normally, when we training our controller, we normally do at low fidelity or middle fidelity models, which can largely reduce the computation cost. And when we do the test, we do the test as the high fidelity model. As we said, we just developed a GPU-based high fidelity simulation model. This can largely reduce the computation time when we do the test.
Great. Thank you very much, both of you. Really interesting. Yeah, very exciting to see where this goes. Thank you very much, everybody. We will circulate the slides and the link to the recording at some point, probably over the next few days. Thank you all. That's it from us.
Thank you.
Thank you.